Leading-edge chips require billions of devices, multiple layers of patterning, and complex power delivery structures. Scaling is no longer governed strictly by device physics and lithography hardware. Producing these structures requires a dense, coupled, high-performance computing stack. Engineers use electronic design automation, computational fluid dynamics, TCAD, and lithography solvers, all of which demand immense compute power before physical manufacturing in a cleanroom facility ever begins. The resulting compute demand is a living workflow graph. To design a chip, engineers navigate a directed acyclic graph containing thousands of heterogeneous nodes. Look closely. They represent rigorous numerical solvers, machine learning surrogates, mandatory human review gates, and license dependencies. Traditional batch schedulers struggle here. They optimize purely for node utilization and batch throughput, blindly bin-packing jobs onto whatever hardware is available. But high throughput does not equal high quality of result. If a scheduler pushes a fast, low-fidelity surrogate model through the queue to save time, the run finishes quickly, but it leaves you with high uncertainty in the final design. To coordinate this environment, the system needs a meta-control layer. It needs to understand the physics, the scientific value, and the dependencies of the entire workflow to route compute safely. The primary bottleneck in semiconductor innovation is no longer whether an isolated solver can execute. It is the high-dimensional orchestration of these coupled workflows. To solve this orchestration problem, we look at the mathematical state of a single node in that graph. It has multiple dimensions. At any moment, it tracks compute load, memory pressure, solver residual, license availability, quality of result, and security posture. Now scale that up. Tracking these variables across all process corners, physics models, and design variants creates a state space that explodes. It scales exponentially at O of n to the d. Traditional matrices or vectors fail here. They cannot capture the cross-domain dependencies hidden across thousands of concurrent operations. This is where the Predictive Tensor Control Plane, or PTCP, comes in. It is a layer designed exclusively to ingest this multidimensional telemetry. The PTCP converts all that joint workflow telemetry into a single unified probability tensor. Then, using Tensor Train decomposition, the system compresses this massive tensor into a continuous chain of smaller interconnected cores. This mathematical compression reduces the storage and processing requirement from an intractable O of n to the d down to a manageable O of d nr squared. What you get is a mathematically compressed representation that provides a predictive pattern-of-life forecast for the entire HPC fabric. By tensorizing the workflow, an impossible state space becomes a manageable mathematical object, perfectly preserving the critical dependencies. To use this compressed tensor, we apply an operational framework called Tensor-Network Quantum Gravity, or TNQG. This is not a theory about physical spacetime. It is an operational reconstruction program for our data. We take the compressed tensor train network and translate it into a continuous topographical manifold. The rule here is strict. The underlying information structure strictly dictates the physical shape of this manifold. Workflow edges with strong data coupling manifest physically as very short distances on the manifold. Conversely, systemic bottlenecks like slow network links stretch into long restrictive cuts across the topography. For example, if an EDA routing tool and a thermal packaging solver share critical dependencies, their informational coupling pulls them close together in this geometry. This structure allows us to spot defects. We look for areas of extreme, sudden curvature on the computational manifold. Sudden drops in model validity, IP anomalies, or critical process window discontinuities manifest immediately as severe, fractured topology defects. The diagnostic value is immense. Instead of parsing millions of raw text logs, the scheduler visually sees a geometric landscape of workflow health. By inducing this geometry, TNQG transforms HPC scheduling from a blind list sorting task into a predictive visual navigation problem. Once we have mapped the workflow, we need an objective function to drive the control plane's actual decisions. This optimization target dictates how the system chooses the best workflow path. The primary goal is to minimize expected downstream loss and actively mitigate extreme tail risk, represented by the conditional value at risk term. Then we subtract the expected information gain. The system mathematically rewards paths that collapse uncertainty the fastest. This is the value of information principle. Scarce compute resources, like GPU clusters, are selectively routed to high-curvature, high-risk areas of the geometry to provide clarity. But there is an absolute, non-negotiable constraint: the projection into the safe set. In a lithography scenario, the system attempts to route a mask synthesis clip to an external GPU cluster. The safe set actively blocks this action to prevent exporting restricted IP, forcing the optimization to find a legally compliant path. Bounded actuation ensures that while the AI optimizes aggressively, it can never bypass the validation envelope, license limits, or legal constraints of the fab. Bringing all these mathematical and geometric components together reveals the complete operational system structure. This diagram outlines the full PTCP plus TNQG reference architecture. It relies on a continuous feedback loop, ingesting raw telemetry, compressing it via PTCP, reconstructing the geometry via TNQG, and applying bounded actuation back to the HPC substrate. It is crucial to define the operational boundary here. This architecture does not replace rigorous domain solvers, like Maxwell equations or density functional theory. There is a strict separation of duties. Domain solvers compute the physics, while this control plane acts as the meta layer orchestrating their network interactions. The core scientific claim of this architecture is testable. Its success must be measured against rigorous baselines, not theoretical commisses. In peer review, the true metrics of success are measurable reductions in P99 workflow tail latency and the earlier detection of costly lithography hotspots. The ultimate business value is a higher throughput of validated manufacturable process windows per GPU hour invested. Next-generation semiconductor innovation requires this predictive, geometric meta-control layer to translate raw exascale compute power into reliable, secure